Hello friends, this is Hidden World. Today we are traveling into deep time to uncover Ice Age mysteries that still shape California. We will walk ancient shorelines now hidden by waves, meet giants that once grazed where freeways run, open the quiet pages of tar-filled pits, and ask what all of this says about the future. Keep your imagination ready and your feet warm. The past is colder than you think, but it is full of life. Part 1. How California looked 20,000 years ago. Picture a map of California with the ocean pulled far away from the modern coast. Global sea level is lower by about 120 meters because so much water is locked up in continental ice. What we now call the continental shelf is dry ground. Kelp forests grow along a shoreline that lies tens of kilometers farther out. The Channel Islands are not a scattered chain. They are one large island called Santa Rosa, a single mass of land that once held rivers, oak woodlands, and grasslands. On a clear day, you could have walked across wide beaches and shallow channels and never known that your footsteps would be underwater in the future. Turn east and look toward the Sierra Nevada. During the last glacial maximum, many high valleys are filled with moving ice. Cirques that hikers love today are the cradle of small glaciers then. U-shaped valleys and polished domes grow under a slow grind that lasts for thousands of years. In a few basins, small glaciers extend down to about 2,000 meters above sea level, leaving moraine ridges that still hold lakes and meadows. Summer days are cool and short. Winter nights are long, and wind stacks snow into cornices that glow blue at their broken edges. The deserts of the interior are not empty, they are wet. You can draw a chain of connected lakes down the spine of the basin and range. The Owens River feeds a series of basins that step down toward Death Valley. Owens Lake is full. Searles Lake is full. Panamint Lake is full. Death Valley itself hosts a long pale ribbon called Lake Manly. At high stands, Lake Manly stretches for more than 100 kilometers from end to end. White shorelines climb the hills above the modern valley floor like chalk lines on a blackboard. These pluvial lakes are a record of stronger winter storms and a jet stream path that sits farther south than it does now. California is a quilt of habitats. Along the coast, the climate is cool and foggy. Inland valleys hold a mix of open grass and scattered woodland. Farther south, near present-day Los Angeles, the landscape is a mosaic that looks part savanna and part scrub, a place where large grazers roam from water to water. North of San Francisco and inland, toward the Klamath and the Modoc Plateau, you find conifer woodlands and open country that feels like a patchwork of parkland. The line between these worlds moves back and forth with each century of wetter or drier weather. When the ice retreats a little, grass surges. When the snowpack grows, wetlands spread and the sound of frogs carries for kilometers on still nights. The rivers are busy. The Sacramento and the San Joaquin run high with meltwater in long spring seasons. Their combined flow builds a delta that spreads farther west than it does today, and their sediment feeds a submerged canyon that later becomes the path of the modern estuary. The Eel, the Russian, the Salinas, and the Santa Clara valleys each host broader floodplains than we know now. Floods arrive on a schedule that feels different from the modern pattern. A single, cool winter may be quiet. The next winter may bring a sequence of deep storm tracks that fill basins and knit wetlands together across the landscape. The state is not frozen from end to end. It is alive with water moving from uplands to sea. When you stand on a modern overlook and try to see that older world, use a few numbers to anchor your view. Sea level is down by about 120 meters. Lake Manly stretches more than 100 kilometers in length. The Channel Islands are one island that is many times larger than the modern chain. If you prefer a near street view, remember that many of the hills around Los Angeles are piles of sand and silt delivered by storms that track along the foot of snow-covered mountains. Every contour you see is a quiet note from the Ice Age orchestra. Part 2. Giants of the Glacial Coast. An ice age is not only ice, it is teeth and muscle and thick coats. It is long tusks and heavy bones. It is eyes that read a winter sky. California holds a full cast of giants, and their stories are written in canyon walls, in tar, and in the silt of old riverbeds. On open ground, the Columbian mammoth is the emblem of size. A large male can reach nearly 4 meters at the shoulder and weigh up to 10 tons. Tusks curve more than 3 meters from tip to tip in a slow arc that frames the head like a question mark written backward. These mammoths favor grass. In a winter storm, they use their tusks like snow shovels to uncover sedges and old seed heads. They travel in groups that leave broad lanes stamped into the crust. When you see a mammoth track in firm mud, it is large enough to hold a bucket. Nearby lives the American mastodon. It is shorter and more robust than the mammoth, with teeth that look like a series of rounded cusps. Those teeth do not grind like millstones. They crush twigs and strip bark. Mastodons walk the edges of wetlands and the brows of groves, feeding on conifer branches and willow shoots. A big mastodon weighs several tons, and a determined individual can reshape a small grove in a season by pushing over young trees and breaking older ones. If a mammoth is the mower of the ancient lawn, a mastodon is the pruner and the bulldozer. The ground sloth adds a new form to the parade. Paramylodon is a giant that can weigh more than 1.5 tons. When it rears on its hind legs, it reaches a height of 3 to 4 meters. It uses long claws to pull down branches and to dig for roots. Its hide is studded with tiny bones called osteoderms that work like built-in armor. At a waterhole, a ground sloth moves with unhurried confidence while birds and smaller mammals give way. In mud near tar, springs, the round prints of sloth feet freeze in time beside the delicate marks of birds. Bison antiquus grazes in herds that are larger than those of later centuries. This bison is about 15% bigger than the modern plains bison. Its horns spread wider and its shoulder hump rises higher. Herds move in wide arcs between seasonal water and fresh green growth. Where herds pause and rest, dung builds up in layers that archaeologists and ecologists later read like a diary. A herd that numbers in the hundreds can cut a trail that lasts for years. Camels and horses belong here as well. North America is the cradle of horses, and several species range across the state before they vanish at the end of the Pleistocene. Camelops, the western camel, browses in open country and can stand as tall as a modern moose at the shoulder. Tracks across lake beds show lines of individuals moving together at a steady pace toward a distant ridge where shrubs break the wind. Predators watch this traffic. The saber-toothed cat is famous for its long, curved canines that can reach 18 centimeters in length. The animals are powerfully built with strong forelimbs and compact bodies. Nearby, a pack of dire wolves moves like smoke across a flat, using teamwork to test the edges of a herd. An American lion, larger than a modern African lion, stalks the margins of a marsh where small streams enter. The list of carnivores is long for a reason. The landscape holds enough large herbivores to sustain many ways of hunting and many ways of scavenging. Each predator leaves a different signature in the bones it drags and breaks. Part 3. Buried Shores of the Pacific. Imagine flying over the California coast during the height of the last glacial maximum. Where you expect waves, you see a wide plain. River mouths cut deep channels into the shelf and braid across sandy flats. Kelp forests cling to rocky points that stand like small capes along a distant line. The Channel Islands are not four separate stepping stones. They are linked into a single island called Santa Rosa. What is now the Santa Barbara Channel is a valley. Winds push dust across open ground and leave faint lines that curve like ripples on a beach. That lost coast is not small. In places, the exposed shelf is tens of kilometers wide. A person on foot could walk from the modern mainland out across dunes and low ridges to the slope that drops to the Ice Age sea. Along that slope, patches of kelp create a sheltered corridor rich in fish, shellfish, and sea mammals. This kelp highway is a natural route for early people who know how to travel along the edge of land and sea. It offers food every few hours, shelter from waves, and a consistent path around headlands and bays. Many archaeologists now think that the first Californians and the first Americans who reached the far west followed this green ribbon. Proof of those journeys is both generous and hard to touch. On land, we have caves and sheltered terraces with tools, shells, and charred plant remains that date to the late Ice Age. On the islands, we have human remains dated to about 13,000 years ago and camps that show repeated visits as climates shifted. Underwater, we have chemistry and physics and good maps that suggest where ancient river mouths lay and where camps would have stood above floodlines. What we do not have in abundance are direct underwater sites with clear artifacts, because the modern ocean has rearranged those places for thousands of years. Still, the buried shores speak. Sonar shows drowned channels that mirror the modern mouths of the Ventura and Santa Clara rivers. Steep banks at the edge of the shelf mark ancient beach scarps. Cores pulled from the seabed bring up pollen and shells that tell us about a colder sea and the plants that grew along the old coast. Even on the modern beaches, storms sometimes expose layers of peat from ancient marshes, a dark stripe that formed when sea level was lower and a river mouth wandered in a wide arc. If you stand on a bluff after a winter storm and look at the ocean, you can imagine homes and trails far out under the white caps. Use a few reference points to make this real. Sea level is about 120 meters lower than it is today. Santa Rosa is many times larger than any modern Channel Island and sits closer to the mainland because the shelf is dry. The shelf holds river deltas and lagoons that are now submerged, and those features likely hosted camps with fish drying racks, shell middens, tulle rafts, and the first true sailors of the California story. Part 4. Giant predatory birds. Look up. The Ice Age sky over California is busy. Among the actors are birds so large that at first you may mistake them for gliders. Teratornis merriami rides thermals with a wingspan of roughly 3.5 to 4 meters. That is wider than a small car is long. Weight estimates cluster around 15 kilograms. The bird has a strong hooked beak and long legs. It can land near a carcass, walk with purpose, and use its bill to tear hide and muscle. Its size lets it dominate other scavengers, and its vision lets it spot food from far away. Even larger is Iolornis incredibilis, a cousin that may reach a wingspan close to 5 meters. Imagine a shadow passing over a dry lake bed and covering a small car. That is the scale. With a body that pushes past 20 kilograms, this bird could soar for hours in strong desert thermals and cross basins without flapping for long stretches. It is not built for lifting heavy prey from the ground like an eagle. It is built for endurance flight and for control on the ground once it lands near a carcass. At a bison kill, You can imagine Iolornis as the quiet authority that tells foxes and coyotes to wait their turn. California condors are present as well, slightly smaller than their modern descendants, but filling a similar role. Around tar seeps and natural springs, vultures and condors create predictable constellations. A dead horse or a stuck deer draws a sky full of wings in under an hour. The speed of that response is impressive. Give a number to frame it. A soaring scavenger can see a rabbit from a kilometer away and can see the glitter of a gathering of other birds from even farther. News of food flies on the air. Predatory birds that hunt actively are also part of the picture. Golden eagles patrol ridgelines and open flats. Short-eared owls haunt grasslands at dusk. But it is the truly large carrion specialists that focus our attention because they capture the scale of the Ice Age. When the bones of a mammoth surface from tar, they are often accompanied by bones of teratons and condors. At Brea, more than 100,000 bird fossils have been recovered, many of them raptors and scavengers. That sample gives us a detailed roster of the Ice Age sky, and tells us that where there are many big herbivores, there must also be many wings willing to clean up. What does a giant scavenger mean for the ground story? It means that carcasses are recycled fast, that nutrients move from a dead bison into the soil through the droppings of birds in a day instead of a week, that disease has less time to spread, and that a big kill signals through the ecosystem with visual and chemical cues that travel for kilometers. The ancient sky is part of the health of the ancient ground. Part 5. Time Coffins at Brea Tar Pits. In the middle of modern Los Angeles sits a window into deep time. The Brea tar pits are pools and seeps of natural asphalt that trapped animals for tens of thousands of years. They are called pits, but for the animals, they behave like glue laid in low spots on a path. A herbivore steps in and slows. A predator pounces and also gets stuck. Over time, bones become wrapped in sticky tar. Dust and leaves cover the surface. Another season passes, and a new layer forms. Repeat that process for thousands of years, and you build a stack of scenes more complete than any written diary. Numbers make the scale clear. Scientists have catalogued more than 5 million fossils from this one site. The collection represents roughly 600 species of animals and plants. There are more than 4,000 individual dire wolves, which makes this site the richest record of the species on the planet. There are more than 2,000 saber-toothed cats. There are hundreds of thousands of small bones from birds, rodents, and reptiles. There are insects, seeds, cones, and pollen. A single block of tar from one area can hold bones of a mastodon, a dozen birds, beetle parts that glint like jewels, and leaves that crumble at a touch. Brea also yields individuals with names and stories. Zed the Colombian mammoth is a famous example, a large male found with tusks more than 3 meters long, a mastodon preserved with parts of the trunk, and soft tissue hints at what these giants looked like beyond bone. Some pits date to near 26,000 years ago. Others are much younger, from the end of the Ice Age, just before the climate lurches into a warmer regime. This range lets scientists compare communities across time and see which species fade early and which persist longer. Why call these pits time coffins? Because they seal information in tiny spaces that exclude air and bacteria. Asphalt is a preservative that records muscles as stains and keeps small bones from weathering. The chemistry even preserves ancient DNA under the right conditions. When technicians clean a fossil under magnification, they are not just exposing bone. They are exposing a system of relationships preserved at a level of detail that is rare in the world. The pits also reveal behavior. Bite marks on bones show where predators worked. Punctures align with the tips of saber-toothed canines. Cut marks, in a few cases, show that people interacted with carcasses late in the record. There is also a cautionary lesson. Brea shows a community rich in large mammals that disappears quickly on a geological clock. Many of the largest animals vanish between about 13,000 and 11,000 years ago. That is 100 or 200 human generations. A student can walk through a museum gallery in a morning and watch giants disappear in minutes. The record is a reminder that abundance can end fast when pressures change. Part 6. Catastrophes and climate jumps. The end of the last ice age is not a smooth slide into our modern world. It is a staircase with steps and landings, and some steps are steep. Around 14,600 years ago, global sea level rises at a pace that reaches several centimeters per year for a few centuries. This pulse floods low river valleys and erodes new shorelines into cliffs that had stood above water for thousands of years. Estuaries expand, barrier islands shift. For people living by the sea, the change would be visible within a lifetime. A child could draw a different coastline from the one their parents knew. Between about 12,900 and 11,700 years ago, the climate reverses and cools again. This short, cold snap arrives quickly and ends quickly. In California, the signal likely shows up as changes in storm tracks and rainfall patterns, not as a return to full glaciation. Lakes that had been dropping may stabilize for a time. Streams carry more sediment one decade and then less the next. Wildfire patterns shift. Plant communities move north or upslope at different speeds depending on soil and local moisture. Across North America, the large animals pay a price. By the time the climate warms again, roughly 3 out of 4 species heavier than 50 kilograms are gone. In raw numbers, that is more than 30 genera on the continent. In California, the list includes the Columbian mammoth, the American mastodon, the western camel, horses, the short-faced bear, some large cats, and the great teratons. Smaller animals do better. Deer survive. Pronghorn survive. Coyotes thrive. Ravens and condors adapt to a world with more human trash and fewer fresh carcasses from giants. Why do the giants vanish? Scientists present 2 main explanations and a compromise that includes both. The first explanation is climate. Rapid swings stress large herbivores that need a lot of food. A drought of a few decades cuts calf survival and drives herds into valleys where competition is fierce. The second explanation is people. Humans arrive with better tools, better teamwork, and the ability to learn fast. Even low hunting pressure can push slow-breeding animals into decline. The compromise is that climate sets the stage and people deliver the final push. The truth may be different for each species and each valley. The exact mix matters for our future because it shows how fast a rich community can shrink when 2 pressures combine. A lake that drops a few meters removes a ribbon of green. A new predator adds stress to already thin margins. In under 1,000 years, the balance tips. When we look at today's challenges, we can borrow a number from the past. A change that lasted a few centuries at the end of the Ice Age changed the map of a continent. A century of choices now can change the map for the next 1,000 years. Part 7. Could an Ice Age return, and when? This is a favorite question. The short answer is yes. Large ice sheets will return someday, but not soon on a human clock. The long answer is a story about the dance between Earth and the Sun, and about the way human choices now alter that dance. Earth does not orbit in a perfect circle. The tilt of the axis and the wobble of that tilt change slowly through cycles that range from about 23,000 to about 100,000 years. These cycles change how much summer sunlight falls on high northern latitudes. When summers are slightly cooler there, snow that fell in winter is more likely to survive, and small glaciers can grow. Over tens of thousands of years, those small glaciers can become ice sheets. When summers are stronger, the opposite happens and ice retreats. These orbital patterns are a metronome for the pace of glaciations and the warm periods between them. Before industry, with carbon dioxide near 280 parts per million, some models suggested that the next slow drift toward glaciation could begin within the next several tens of thousands of years. With modern carbon dioxide near 420 parts per million, the story changes. The added greenhouse effect acts like a blanket that keeps summers warmer in high latitudes. Several studies suggest that high greenhouse gas levels can delay the next glacial inception by 50,000 years or more, possibly by 100,000 years. That means our current warm interval may last much longer than it would have without our emissions. Numbers help here too. A typical glacial cycle over the last 800,000 years lasts around 100,000 years. Ice builds in a slow curve for roughly 80 to 90,000 years, then melts back in a quick swing that lasts 10 to 20,000 years. We are living near the top of one of those warm swings. If we blindly follow the old rhythm, the next cool down might have started well after the year 50,000. With our added greenhouse gases, the cool down may start far later. The exact timing depends on what we do in the next few centuries. Could smaller regional glaciations appear sooner? In mountain ranges like the Sierra Nevada, local glaciers respond to local climate. If winters become much snowier and summers much cooler in a future century, small glaciers could grow again in some cirques, even while the planet as a whole is warm. But the return of continental ice that pushes sea level down by 100 meters is a different scale of event, and current physics says that is far away on any calendar we use for city planning. This is not only a story about delay, it is also a story about informed choice. Our ancestors did not get to pick the shape of the last glacial maximum. We do have a say in the climate of the next few hundred years. If we keep coastal wetlands healthy and give rivers room to move, we make room for nature to buffer storms as sea level climbs by meters this century and the next. If we plan cities with the memory of ancient channels in mind, we avoid building on soil that will sink under long, wet winters. The Ice Age offers a library full of case studies. We can open that library any day. When you hold all of this together in your mind, California becomes a living museum and a laboratory. You can stand on a bluff and see a drowned valley. You can visit a museum and see the face of a mammoth that walked a few kilometers from where you park your car. You can look up and imagine a bird with a 5-meter wingspan circling on a thermal. You can kneel beside a tar seep and watch bubbles rise from a trap that has worked for tens of thousands of years. You can trace shorelines that appear and vanish with climate pulses that move sea level by meters in a lifetime. You can see how communities recover after shocks and which species manage to adapt. We began by asking how the Ice Age still shapes California. It shapes the coast, the soils, the wetlands, and the way storms draw lines across the sky. It shapes the locations of cities and the routes of freeways. It shapes the find spots of fossils and the places where kids will stumble on a tooth while planting a tree. It shapes our imagination because we are storytellers who like to know what was here before we arrived. And it shapes our decisions because knowing the past gives us better odds of building a future that can carry our children through the next set of changes.